Hello students, welcome to our physics revision class. So as you can see, we are going to start to revise Unit 1, which is about thermodynamics. So if you remember, before we define what thermodynamics is, we have seen that the word thermodynamics by itself comes from two Greek words. The first one is thermos, which means heat, and the second one is dynamis, see? So which means power. So simply, thermodynamics is a branch of physics that studies about the conversion of energies from heat to other forms or vice versa, okay? So we can simply define thermodynamics as a branch of physics that studies about energy conversion between heat and other forms of energy. So, in order to understand the basic concept of thermodynamics, I think it's important to define some of the important terms like internal energy, what do you mean by temperature, even what do we mean by heat for that matter, okay? So internal energy simply is defined as the sum of the kinetic and potential energies possessed by the particles of a system. So the system is the thing that we are studying in thermodynamics, and the surrounding is everything that's out of the system, okay? So internal energy for a system, for example, our system might be water in a container. So the particles of the water are in some sort of random motion. As a result of that, the particles possess what we call kinetic energy. So because their state of confinement, because they are confined in a state, in a given region, they also store what we call potential energy, stored energy. So as a result, the particles of water possess both kinetic and potential energy. So our system is the water. So the internal energy of water is simply the sum of the kinetic and the potential energies possessed by its particles. Okay? So another important term we need to define is temperature. So in lower grades we have defined temperature as the measure of the amount of hotness or coldness of a system. But I think we need to have a more appropriate definition for temperature, because in physics, when we say simply a hot object, it means high temperature. High temperature means fast-moving particles. Fast-moving particles simply means high kinetic energy, okay? So we can redefine temperature simply as the measure of the amount of kinetic energy possessed by the particles, okay? Temperature is, as you know, one of the 7 fundamental physical quantities. It's measured using 3 different scales. There is a Celsius scale, the Fahrenheit scale, and the Kelvin scale. And the Kelvin scale is the absolute thermodynamical scale. And we have a temperature which we call absolute zero. So absolute zero is the temperature at which all the random motion of the particles of a system ceases. Okay, it stops at this temperature. Okay. And another important thing about temperature and heat is heat and temperature are not the same things, but they are very related, because we cannot talk about heat if there is no change in temperature between two systems or points in a system, okay? So heat is simply defined as energy that's transferred from one point to another point, or from one object to another object, because of the change in temperature. It's an energy in progress, all right? So for example, if two objects are at a different temperature, so the particles of the, for example, if this is 100 degrees Celsius and this is 0 degrees Celsius, then the particles between the two systems start to collide with each other. As a result, there will be a net transfer of energy from state A or system A to system B. This net flow of energy due to the change in temperature is called what we call heat energy. So this process continues until the two systems attain the same temperature, so that there will be no net flow between them. So when they do that, when they attain the same temperature, then we say they are in thermal equilibrium. So thermal equilibrium simply is a condition in which two systems attain the same temperature, so that there is no net heat flow between them. All right? So then we can come to the zeroth law of thermodynamics. So the zeroth law of thermodynamics simply says that if two systems are separately in thermal equilibrium with a servo system, then they are definitely in thermal equilibrium with each other, okay? So that means if TA is equal to TC, that's they are in thermal equilibrium, and if TB is equal to TC, then definitely TA will be equal to TB. The TA and TB will be equal, or the two systems, system A and system B, will also be in equilibrium. Okay? Then it's important to, I think, to revise on the kinetic theory of gases. And we have, as you remember, we have take some assumption for an ideal gas. Some of the assumptions for an ideal gas is that when the particles of the ideal gas, they don't interact with each other. As a result, they only possess kinetic energy, and laws of motion are applied during collision. Kind of collision between particles of an ideal gas is perfectly elastic, and most important assumption for ideal gas is that there is a random distribution of velocity. Okay, so using these assumptions, we come up with some mathematical expressions that relate the molecular variables with the microscopic variables with the macroscopic ones. Okay, for example, we can determine the RMS speed or the average speed with which the particles of an ideal gas move using the pressure of the gas and the density of the gas. And we can also determine the average kinetic energy possessed by the particles of the gas using this mathematical expression. So average kinetic energy is equal to 3 over 2 kT, where K is the Boltzmann constant. So as you can see from this, the kinetic energy possessed by the particles only depends on one variable, that's the temperature. Okay, that's how we define temperature here. And we can also find an expression for the internal energy of an ideal gas. So the internal energy of an ideal gas is 3 over 2 nR change in T, where n is the number of mole of the particles and R is the universal gas constant. Again, as you can see here, the internal energy of an ideal gas depends on only temperature. Okay, only temperature. So next up is about first law of thermodynamics. So the first law of thermodynamics is nothing but the law of conservation of energy that contains heat energy. So we know that the law of conservation of energy simply states that energy of the universe is constant, or energy can neither be created nor destroyed. It can only be transferred from one form to another form. So for example, if we have a system, it can be gas, okay, at some initial state with Ti, Vi, and Pi. These are called state variables. And if heat is supplied to this system, then the system will utilize this heat in two different ways. One, it will increase the internal energy of the system. And two, it will provide the system with sufficient energy so that the system can do some work, mechanical work on its surrounding. Okay, so from the law of conservation of energy, all the heat supplied to the system are utilized. So energy is conserved. Okay, so mathematically, the first law of thermodynamics is stated as Q is equal to change in internal energy plus work done. Okay, so this is one way to put it. But in texts, they use this expression. They are the same, but there's some kind of sign convention that we use with these expressions in solving problems. So we prefer to use this one, and this expression, the sign convention is simple. When heat is added to the system, Q is considered a positive. When heat is removed from the system, we consider Q as negative. All right? So concerning the work done is considered a positive. It's work done by the system. And the work done is considered as negative. It's work done on the system. Okay? So this is how we can use first law of thermodynamics, especially in problem solving. So we can apply the first law of thermodynamics for different thermodynamical processes. The first kind of thermodynamical process is called adiabatic process. Adiabatic process is a kind of process which involves no heat transfer between the system and its surrounding. So Q will be 0. If Q is 0, then you can see that the change in internal energy is equal to the negative of the work done. That means the internal energy of the system can only be increased when there is a work done on it or work done by it. So since there is no heat transfer to the system. Second type of thermodynamical process is what we call the isothermal process. Isothermal process is a kind of process that takes place at a constant temperature. So if the temperature of the system is constant, then the change in temperature will be 0. If the change in temperature is 0, then there will be no change in internal energy of the system. So here all the heat supplied to the system will be converted into work done, okay? So we can calculate the work done for an isothermal process by this mathematical expression. Work done is equal to number of mole times R times T times ln of the natural logarithm of V2 over V1, okay? So the third process is isochoric. Isochoric is a kind of process that takes place at a constant volume. So if volume is constant, then the change in volume is zero. If the change in volume is zero, we know that the work done is calculated by P times change in V, then the work done will be zero. Then all the heat transferred to the system will be converted into the change in internal energy of the system in isochoric process, right? So the fourth kind of process is called isobaric process. Isobaric process is a kind of process that takes place at a constant pressure. If the pressure is constant, then the work done is expressed using this expression. So the first law of thermodynamics will have a form Q is equal to change in U plus P times change in V if this is work done by the system. But if work is done on the system, then Q will be change in U minus P times change in V, all right? So there is another kind of process that might take place in a thermodynamical system. If the thermodynamical system is an isolated system, so a system is said to be isolated if it's not interacting in any way with its surrounding. So if it's not interacting with its surrounding, then there is no heat transfer into the system or out of the system. Then there will be no work done on the system or by the system. So then the internal energy of the system remains constant for an isolated system, okay? But this is kind of an ideal system because there is no such thing as an isolated system in the universe because everything in the universe interacts with each other, okay? So there is even a saying that the only isolated system in the universe is the universe itself, all right? So there is also a different kind of process which we call a cyclic. As the name indicates, a kind of process that repeats itself over a certain amount of time. So the system will get back to where it started, so it will get back to its original state. So since internal energy is a state variable, at the end of the day, the internal energy of the system will remain the same. So the change in internal energy for a cyclic system, for a cyclic process is zero. Then if at any point in the process heat is supplied to the system, then all the heat supplied to the system will be converted into a work done, right? It will be converted into a work done. Okay. Now let's go back to molar heat capacity. So molar heat capacity is simply defined as the amount of energy required to change the temperature of 1 mole of a gas by 1 degree Celsius or 1 degree Kelvin. So actually gas has two kinds of molar heat capacities because the amount of energy required to heat gases at constant pressure and at constant volume is different. But for solids and liquids, they have the same, okay? They only have specific heat capacity. So molar heat capacity at constant pressure minus molar heat capacity at constant volume for an ideal gas always gives us the universal gas constant R, and we call this the Mayer equation. Okay? So if you take a sample of gas and try to calculate the ratio of Cp to Cv, you get a constant, okay? That constant might be 7 over 5 or 5 over 3, depending on the kind of the gas. If the gas is a monoatomic gas like helium, okay, then you get 1.67. But if like it's oxygen, a diatomic gas, then the ratio of Cp to Cv will be constant, that is 7 over 5 or 1.4, okay? So this is all about the first law of thermodynamics. So the next topic is about the second law of thermodynamics. So before we state what the second law of thermodynamics is, or it says, it's important to define entropy. So entropy is one of the most important concepts in physics, and entropy is simply defined as the measure of amount of chaos or disorderness in a system. So in physics we have two ways of approaching entropy. The first one is statistical. So in statistically we can define entropy as S is equal to K times ln of omega, where omega is the number of different ways in which the system can be rearranged, okay? The particles of the system can be rearranged. And thermodynamically, we can also calculate the change in entropy as Q over T, right? So the two approaches. So normally the second law of thermodynamics states that there is no process in which there is an overall decrease in the entropy of the universe. That means the entropy of the universe always increasing. So we can simply state the second law of thermodynamics using these equations. The entropy of the universe is either constant or greater than 0. Okay? No process is possible in which it can decrease the entropy of the universe. It can decrease the entropy of the universe. Okay? Actually, the second law of thermodynamics have different forms. This is one of the forms in terms of entropy. But when we come to heat engines, we can have a different kind of statement for the second law of thermodynamics. Okay? So let's define what we mean by heat engine. Okay? Heat engine is simply a device that converts heat energy into a useful mechanical work by extracting heat energy from a hot source. Then it converts some of the heat from the hot source into work done, and it then releases some of the rest of the energy to a cold sink. Okay? So this is what a heat engine looks like. So heat engine is a device that works with the application of the first and second law of thermodynamics. So the first law of thermodynamics can be applied. So QH, which is heat is transferred from the hot source to the engine. Some of it will be work done and some of it will be transferred to the cold sink. As a result, the total amount of energy in the system remains constant. Heat energy is conserved. But when we apply the second law of thermodynamics for heat engine, since converting all the heat energy from the hot source into work done decreases the entropy, it's not possible to convert all the heat energy from the source to a work done. Okay? We can put it this way. No process is possible, or a complete conversion of heat into work is impossible. Okay? This is a different approach for the second law of thermodynamics. A complete conversion of heat into work is impossible. So we can have different kind of heat engines, from a very simple one to a very complicated one. But we can calculate the efficiency, their working efficiency, using these mathematical expressions. You know that efficiency is determined how much useful work is done. So mathematically, efficiency is equal to work output divided by the input energy multiplied by 100%. So efficiency is equal to 1 minus QEC over QH multiplied by 100%. So we can maximize the efficiency of heat engines using this expression. This is an expression for the efficiency of a Carnot engine. A Carnot engine is an ideal kind of heat engines which works with a working substance that is an ideal gas. Okay? So in order to find the maximum theoretical efficiency of our heat engines, then we have 1 minus Tc over Th multiplied by 100%. You know that Tc is the temperature of the cold sink and Th is the temperature of the cold sink. So from this expression, for our theoretical maximum efficiency to be 100%, Tc has to be 0 Kelvin, okay? But according to the third law of thermodynamics, it's not possible to reach at this temperature, right? So nobody or nothing can reach this to this temperature. As a result, we cannot have a heat engine which is 100% efficient. So this is all about thermodynamics. I hope you find this revision useful. So until we see on our next episode, stay safe.